Day 7, homework problem number 22, AP Physics. This is a classic Atwood's machine, and we're assuming a frictionless pulley, massless rope. One of the keys is are the free body diagrams for each mass, trying to make the vectors approximately the right length. For the small mass, T is greater than W sub 1, the weight of the small mass. The two T's are the same, the tension is the same everywhere in a string, a massless string over a frictionless pulley. That's why you need to call this T sub 1 and T sub 2. It stands for the force or tension in each portion of the string, so to speak. But for mass number 2, W sub 2 is greater than T. And the concept here is drawing the diagram and then applying Newton's second law, F net equals ma. So on the left-hand side here, what we did in class, I have this written down with respect to my notation here. Instead of using F sub T, I'm using T for tension. And what we did in class, we proved the first part of this Atwood's machine relationship, the acceleration of the system, by solving each of these two equations on the left here for T, setting them equal to each other using the algebra and plugging in mg for the weights, m sub 1g for the smaller mass, m sub 2g for the larger mass. And that's how we did part A, so we did that. Now part B here, what you can do is take those two equations that are the application of Newton's second law for each particular of the two hanging masses, solve for A. So if I do that over here on the bottom left, I get, and once again, A is the same for both masses. You know, one's up, one's down, but we've taken care of all the negatives, like I mentioned in class, by simply doing big force minus small force for each of the two masses already. So the negatives have all been taken care of. Anyway, so over here for the small mass, we have A equals T minus m sub 1g, because that's the weight. I substituted m sub 1g in for the weight, divided by m sub 1. So I moved the m sub 1 over and then substituted the value m sub 1g in for the weight. And then for the large mass, similar idea. I'm going to move the m sub 2 over and then substitute for w sub 2. W sub 2 is m sub 2g minus t. That's the original left-hand side of that equation, divided by the m sub 2. So that's a little substitution in algebra. So those two equations right there are both equal to A, so they both must be equal to each other. So I'm going to set those two equal to each other. In other words, over here I have T minus m sub 1 g over m sub 1 equals m sub 2g minus t all over m sub 2. So bottom line is you cross multiply and do algebra and to isolate the t. So if I cross multiply, I end up with m sub 2t minus m sub 1 m sub 2g equals m sub 1 m sub 2g m sub 1 m sub 2g minus m sub 1t. Wow, m sub 1t. Just fit that in there. That says minus m sub 1t. If we move things around now, I'll move both terms of the t's to the left-hand side. So it's going to be m sub 2t, which is still there, and that little thing that's kind of off the screen here on the right, it's minus m sub 1t, but now on the left-hand side it'll be plus m sub 1t equals, and I'm going to do a little bit more algebra now. If I move that m sub 1, these are all lowercase m's, m sub 1, it's on the left-hand side, it's minus m sub 1, m sub 2g, and move it over, it's going to be plus, but those are both the same, so it becomes equal to 2 m sub 1, m sub 2, g, because m sub 1, m sub 2g plus m sub 1, m sub 2g is 2 m sub 1, m sub 2g. Then I factor out the t on the left-hand side here, so it will be t times the quantity m sub 2 plus m sub 1 equals 2 m sub 1 m sub 2, m sub 2g. And then basically there's one step left to get the answer. so I'm off the screen here, but that basically, one more step gets you this up here on the upper left. The force of tension, I call it T in this case, is 2 times the product of the two masses divided by the sum of the two masses all times little g. And there's a couple of extra notes down here. It says, and I'll go to blue, if m sub 2 is twice as big as m sub 1, what is the acceleration? So I'm going to plug into the acceleration equation. I'm going to plug into this equation. I'll circle it with blue. If I symbolically do that, I have a equals, okay, plugging in 2m sub 1 for m sub 2. It'll be 2m sub 1 minus m sub 1 all over 2m sub 1 plus m sub 1 all times g. So algebraically here on the top, 2m sub 1 minus m sub 1 is just m sub 1. At the bottom, 2 plus 1 is 3m sub 1 g. And since the m sub 1's cancel out, you end up with the acceleration of this particular system when you have one mass twice as big as the other mass is 1/3 normal gravity's acceleration. The next part of this is, when is a equal to 0? When is a equal to 0? Well, a is equal to 0 when the two masses are nearly equal in size. You can see that from this blue circled equation. In the numerator, you have m sub 2 minus m sub 1. As m sub 2 and m sub 1 approach equality, the difference between m sub 2 minus m sub 1 becomes close to 0. If you take 0 divided by anything, you get 0. So you end up with, the closer the two masses are, and just makes common sense as well, the closer the two masses are, the closer the acceleration is to 0. But what about now, and this is a little bit of different notation, down over here in the question, what does this mean? M sub 2, well, what that means is m sub 2 is much, much greater than m sub 1. So what happens if m sub 2 is really big and m sub 1 is really small? Or, for all practical purposes, m sub 1 is close to 0. This is, it's so small, it doesn't make any difference. Well, if m sub 1 is so small, it barely has any mass, so that blue equation, or the acceleration equation, which I have circled in blue, becomes the acceleration equals, essentially m sub 1 is, for all practical purposes, 0. In other words, m sub 2 is really big. It's not 0, but so big that when you subtract it, it becomes m sub 2 minus 0. Let's just call it 0 for a second. Divided by m sub 2 plus 0. Such a small number, it makes no impact on m sub 2 times g. Well, it's just going to be m sub 2 over m sub 2. So in other words, a becomes g. In other words, when one mass is really, really big, which makes sense, it's like free fall. The other mass is not really slowing it down or causing any resistance to acceleration. So acceleration is equal to g. The closer the two masses are equal to each other, the acceleration goes to 0. It's a constant velocity problem. Either they stay at rest if they're at rest, or they will fall. One will go down, one will go up with constant velocity and no acceleration.